I've noticed that I've had a couple of people ask me questions about question 9 on the capacitors quiz. And I realize that because we've done that stuff online, I don't think that we got a good understanding of how to deal with the maths, although the formulas were in the PowerPoint. We obviously didn't get a chance to do any examples, so I thought I would just do a quick video this morning and run through how, for in particular question 9 of that quiz, how we need to go about doing that. So I'll run through this example on the board here, which will be essentially exactly the same as what you've got in question 9. Obviously the values will be different. I've inserted my own values there. So the question itself, question 9, asked us if we have a capacitor and resistor in series with each other, and we're given the value for the capacitor, the value for the resistor, and the voltage that will be supplied. So I have drawn a diagram on the board here. So the numbers I'm going to use, I've got a 275 volts, a 1800 ohm resistor, and a 3000 microfarad capacitor. Okay, so the first part of that question says to calculate the time constant of the circuit and enter it in Canvas. So the time constant, if you remember, T equals CR. So the time constant equals the capacitance times the resistance. So my capacitance is 3000 microfarads, and the resistance is 1800 ohms. Now that 3000 is microfarads, so we need to convert those units. So I can either multiply by 10 to the negative 6, or perhaps an easier way for you is to divide the entire equation by 1 million. So if you're watching this, I recommend you grab your calculator out and follow along with me. I've already calculated all these, so I'll just tell you what the answer is. So 3000 times 1800 divided by 1 million is equal to 5.4. That's the answer there, 5.4, and that answer is in seconds. So the time constant for this circuit that I've drawn here is 5.4 seconds. What does that mean? That one time constant, if you recall, is the time it takes the capacitor to charge to 63%. And that is 1/5 of the total charge time. So the total charge time would be 5 time constants. So the answer that we're looking for in this question is 5.4. Obviously, when you're doing your one, you substitute in the values that you're given in that quiz. Okay, so question 2 then, or second part of that question, it says to calculate the current. Okay, so this one is nice and easy. This is something we should have done 1,000 times before, but my current is going to be I equals V over R. Just like any resistive circuit, we just follow Ohm's law on this one. So V over R, in this case, 275 divided by 1800. And the answer there, 275 divided by 1800. The answer for my one is 0.153 amps. Now, as I mentioned yesterday, there's a Google form. There's a link to a Google form in your quiz. This is where I want you to put the answer. And that Google form is going to ask you to insert those values that you're given in your test. That's just so when it gets to me, I can do those calculations without having to go back into your test. Then you're going to write in the answer for current. In this case, 0.153 amps. Now, I've had a look at a couple of these. A couple of people have submitted the Google form already, and I've noticed an error, that same error on both of them, which has confused me a little bit, where both people have come up with the correct answer, but they've given the wrong units, and they've written, if they were using these values, 153 amps rather than 0.153. I'm not sure how that's happened. So if there's something amiss here, and you're watching this video, if you can see why that's happened, is it maybe just a coincidence that both of those people have made that same error. If not, don't know. But if you're seeing something wrong here, shoot me a text and let me know. Okay, so the answer that we're entering here is going to be 0.153 amps. Obviously, again, your question will be different. However, this is the process to follow. Okay, next one, part 3 of that question. Calculate how long it would take to fully charge the capacitor. Right, so we worked out in the first part of the question our time constant. So our time constant was 5.4 seconds. And remember that our charge time is just equal to 5 times the 5 time constant, so 5t. So this one's really easy. So the answer is going to be 5.4 seconds times 5, which equals 27 seconds. 27 seconds is the answer for part 3 of this question. That is my time constant times 5. That is the time it will take to fully charge the capacitor. Okay. Now it seems like so far we're okay with those particular questions, or mostly okay. I think it's the last one that's going to be an issue. That is, you need to draw a graph, and it's asking you to plot the resistor voltage and the capacitor voltage from 1T to 5T. I've additionally put in the Google form. If you look in the Google form, this says that you need to fully label your graph, and I've said that fully labeled means that I want to see those voltages at least 1T and 5T. So I want you to label on your graph what the voltage is on the capacitor at 1T and 5T, and what the voltage is on the resistor at 1T and 5T. So this one's a little bit confusing because we didn't really talk about that resistor voltage. So what we're talking about here is the capacitor voltage. We talked about that a little bit, right? We said that that capacitor voltage is going to rise as the capacitor charges. And what we know about that is that at 1T, or one time constant, the capacitor will charge up to 63%, and at 5T it would be fully charged. So that tells me then that at 1T, the capacitor voltage will be 63% of the applied voltage, and at 5T the capacitor voltage will be the same as the applied voltage. So that should be pretty simple. And when it's fully charged, obviously it's got to be the same as the supply voltage. It charges up to the supply voltage. It's never going to get higher than that because the supply can't give you any more voltage. And we know that 63% is the number that it'll charge to at 1T. And as I said, I want you to label on there at least the 1T and the 5T. So let's have a look at how we're going to do that graph. So here's my graph here. On this side, we're going to have volts. And on the bottom, we're going to have time. So we'll just label that. I'm just going to make some fairly arbitrary labels here. I'm not particularly concerned whether you're measuring this 100% accurately. What I want to see is that the calculations are correct. So it needs to be tidy, but I'm not going to lose my mind if I'm not going to lose my mind if all the numbers aren't exactly accurate and the spacing is not particularly accurate. Just make it tidy. So on the bottom, we're going to have 1T, 2T, so on and so forth. And I'm just going to add in here that my 1T is 5.4 seconds and 5T was 27. Those are the numbers that we calculated just a minute ago. Okay, so what do I need to put on there? Well, we saw the graphs in the slideshow, and we saw those nice curves, right? That we saw that, for example, that initially when we start the charging process, that is, I switch the power supply on, that the capacitor will charge up, as I said, to 63% in that first time interval, that 1t. So if I have a look at what is 63%, if I just do a calculation, 63% of my supply voltage, which is 275, I come up with, let's have a look, 173 volts. So that tells me my capacitor will charge up to 173 volts in that first time interval, 1t. Where does the graph start? It starts at 0. So at the moment that I turn the power supply on, capacitor is going to be at 0 volts. So that means that the line for my capacitor voltage must be starting here. And then at 1t, it's at 63%, which is going to be 173 volts, which is about here, roughly halfway between 150 and 200. As I said, I've made fairly arbitrary marks on there. And then I also know that at 5t, my capacitor will be fully charged. And fully charged in this case means charged up to 275 volts. So I can make a mark at 5t right up here, 275 volts. That's 175 there, 275 there. That's 173. And I can just draw a nice smooth curve that matches those ones we saw in the slideshow. It should look like that, and in fact, if I plot all those points along there, it does. If I just plot the 2 points, I still get a fairly accurate gauge, and we can see there where those numbers line up with my axes. Okay, and then so the last part of that, which was the perhaps the bit that we didn't go into, is voltage across the resistor. Now, when we're looking at voltage across the resistor, well, how do we know? How do we know what the voltage across the resistor is? What does that mean? So normally, if I just had a resistor in series, or just a resistor across my power supply, and I measured the voltage across the power supply, across the resistor, that's the same as measuring across the power supply. It's going to be, in this case, 275 volts. If I put a multimeter across the resistor, ignoring that capacitor, it will just say 275 volts. However, we've got something that's going to change that equation. We've got that capacitor in there. So let's have a think about this. How does the voltage across the resistor change over the time that the capacitor is charging? Well, we can say, if I were to put my meter across here and here, that I'll get 275 volts, obviously. If I put my meter from here, on one side of the capacitor, back to my 0, when my power supply is not connected, I'll get 0 volts. At the instant that I connect the power supply, and current start flowing, we're still going to have 0 volts across here. Not for very long, but I will have 0 volts across the capacitor. As the capacitor charges up, the voltage across there is going to reduce. And when it's fully charged, my voltage on the capacitor should be the same as the power supply, 275 volts. What does that mean? Well, that means if I measure from there to there, I get 275 volts. So equivalently then, if I measured from this point here back to the positive of my power supply, when the capacitor is fully charged, I would get 0 volts, right? Because that's 275. This is 275. So the difference between them is 0. And we should be able to see then that measuring from this point here to there is the same as measuring across the resistor, because I've just got a conductor straight between there and there, and a conductor between there and there. So that tells me then, at the point that the capacitor is fully charged, there's no voltage across the resistor. Why? Because this is 275, this is 275, so everything along there must be 275, which means 275 on each side of the resistor. So if I measured from end to end of the resistor, there's no difference. 275 on both sides, my voltmeter is just going to say 0 volts. Okay, so that's our starting point then. So if we plot that on the graph, we can say that at 5t, the voltage on the resistor must be 0. We also know that at the point that I turn on the supply, as I said, we've got 0 volts across the capacitor. This is 0 volts, this is 0 volts. So again, thinking about measuring from there to there, I would get 275 volts. So that means that my voltage across my resistor, at the moment that I turn it on, so at 0 on the time axis, that my voltage on the resistor must be 275, which is here. Right, so now we should be starting to build a picture, right? We've got at 0 on my time axis, my voltage on the resistor is 275. At 5t on my time axis, the voltage on the resistor is going to be 0 volts. So clearly, over that time period, as the capacitor charges, the resistor voltage is going to decline. Again, why does that happen? Because as the voltage at this point here rises, the difference between that voltage and that voltage is declining as the capacitor charges, and therefore the voltage, measured voltage across my resistor, is also declining. Well, and so how is it declining? How do I work that out? How do I calculate it? Well, again, if we think about voltage on the capacitor, let's go to 1T. So we already worked out here that at 1T, my capacitor voltage is 173 volts. So if I have 173 volts here, it means I've got 173 volts there. If I've got 275 here, I must have 275 there. So the voltage across my resistor then will be the difference between the applied voltage and the capacitor voltage. So in this case, 275 minus 173. We should also be able to calculate that that voltage is going to be, if this is at 63%, then the voltage on the resistor must be at 37%. But the simplest way to do it is supply voltage minus capacitor voltage. So it's going to be 102 volts. 275 minus 173. So at 1T, that means my resistor voltage must be 100. So now I've got 3 points. I've got my start at 0T. I've got 275 volts across my resistor. At 5T, I've got 0 volts across my resistor. At 1T, I've got 100 volts across my resistor. And we can see that we're going to describe a curve that is the same as this one here, but opposite. So as the capacitor voltage rises, so too the resistor voltage declines, following the same pattern. So it should look exactly the same, but in reverse. That is the voltage across my resistor. And if you draw your diagram like that, we've got our 1, 2, 3, 4, 5T with a couple of numbers on the bottom. Some graduations for my voltage. It will depend on what voltage you have in your question. And then those 1T and 5T points marked with the values, then that's all I'm looking for on that graph. Again, with that Google form, I just need you to draw that. You can take a photo and upload it. If you use your phone for your Google form, that's probably the easiest way to do it, because then you can just take a photo and upload it straight onto that Google form. That way that I can then mark it without having to get your piece of paper. Okay, I think that is it. That covers everything on that question there. If you have any issues, shoot me a text, give me a call or something, get in touch somehow, and I will see if I can help. Thank you very much for your attention.